Assalamu alaikum dear students. Today we are going to cover lecture number 18 of week 9. Today's topic is instrumentation circuits. Instrumentation is an area or field in which you take a measurement of different physical quantities. For example, you want to measure voltage, current, temperature, pressure, these physical quantities that are part of some process in an industry, for example, in which that process, when it is being carried out in an industry, then you want to take measurements of the process at different points. Information of the physical process is very important. So students, جب کسی بھی انڈسٹری کا اگر آپ نے وزٹ کیا ہو تو اس میں آپ دیکھو گے کہ جب بھی کوئی انڈسٹری کے اندر کوئی پروڈکٹ بن رہا ہوتا ہے تو اس کے لیے بہت سارے پروسیسز جو ہے نا وہ چل رہے ہوتے ہیں، اور ہر پروسیس کی اپنی ریکوائرمنٹ ہوتی ہے. اس میں کتنی اس کی ٹمپریچر کی ریکوائرمنٹس ہیں، کتنی کسی بھی پرٹیکولر اس میں کوئی کیمیکل ریئیکشن ہو رہا ہے تو کسی بھی کیمیکل ریئیکشن کے اندر اس کیمیکل کی کیا کوانٹٹی ہوگی، اس کی کنسنٹریشن کیا ہوگی، اس کے علاوہ اس پروسیس کا جو ٹمپریچر ہے وہ کتنا آپ نے رکھنا ہے. تو یہ جتنے بھی فزیکل پیرامیٹرز ہیں وہ ایک کنٹرول فارم میں ایک پروسیس کے اندر آپ کیری آؤٹ کرتے ہیں، اور اگر آپ ان پیرامیٹرز کو اگر کنٹرول نہیں کریں گے تو جو آپ کا پروڈکٹ ہوگا وہ اس طرح سے نہیں بنے گا جیسے سے آپ کو ریکوائرڈ ہے. اس میں ڈیفیکٹس آنا شروع ہو جائیں گے، اس میں پارٹس کریٹ ہوں گے. جو آپ کا کسی بھی انڈسٹری کے اندر آپ نے دیکھا ہوگا کہ کنٹرول روم ہوتا ہے جس کے اندر یہ سارے کے سارے جو پروسیسز ہیں ان پروسیسز کو آپ مانیٹر کرتے ہیں اور دیکھتے ہیں کہ ہر پروسیس جو ہے نا وہ ایک پراپر فارم میں رن کر رہا ہے، اس میں کوئی اپ اینڈ ڈاؤنس تو نہیں ہے، کسی چیز کا جو کوئی کوانٹٹی ہے وہ ایک سرٹن لیول سے ایکسیڈ تو نہیں کر رہی، کسی پروسیس کا ٹمپریچر مینٹین ہے یا نہیں ہے، یا ایک پرٹیکولر جو اس کے جو وولٹیج لیول ہے وہ ایکسیڈ تو نہیں کر رہا، یا اس کو جو پاور ہے وہ وہاں پہ اویلیبل ہے یا نہیں ہے. تو پاور کی مانیٹرنگ، وولٹیج اور کرنٹ کی ریڈنگ پراپر آ رہی ہے یا نہیں آ رہی ہے. تو یہ سارے جتنے بھی فزیکل پیرامیٹرز ہیں وہ آپ مانیٹر کرتے ہیں کنٹرول روم کے اندر، اور اگر کوئی اس میں کوئی چیزیں کوئی بھی پیرامیٹر اس میں ویریشنز ہیں تو یا تو آپ پروسیس کو روک دیتے ہیں یا پھر جو ہے وہ اس کے پیرامیٹر کو دوبارہ سے سیٹ کرنے کی کوشش کرتے ہیں. تو یہ جو انسٹرومنٹیشن کے جو ایریا دیٹ از اے ویری وائڈ ایریا جس میں بہت ساری اپلیکیشنز جو ہے وہ رن کرتی ہیں، اور ان اپلیکیشنز کو کنٹرول کرنے کے لیے آپ بہت ساری الیکٹرانکس ریکوائرڈ ہوتی ہے، جس میں پی ایل سی جو یوز ہوتی ہے بیسیکلی اسکاڈا وغیرہ سافٹ ویئر یوز ہوتے ہیں اسکاڈا کے، اور پی ایل سیز بورڈز ہوتے ہیں، پی ایل سی کنٹرول ہوتا ہے، وہ سارا اس میں انوالو ہوتا ہے. تو پی ایل سی کو جو آپ ریڈنگ اس کو پرووائڈ کرتے ہیں وہ آپ سینسرز کے تھرو اور کچھ سگنل کنڈیشننگ سرکٹس کے تھرو پی ایل سی کو آپ ڈیٹا آپ ٹرانسفر کرتے ہیں، اور پی ایل سی اس کے اکارڈنگلی ڈیسیژن میکنگ کرتی ہے. تو یہ جو انسٹرومنٹیشن جو آپ کے سگنل کنڈیشننگ سرکٹس ہیں وہ کس طرح کے ہوتے ہیں، وہ کن ڈیوائسز سے آپ امپلیمنٹ کرتے ہیں، ان جو سگنل کنڈیشننگ سرکٹس ہیں ان کی کیا ریکوائرمنٹس ہیں. تو کچھ میں اس لیکچر میں آپ کو ایک آئیڈیا دوں گا جو کہ آپ کو ہیلپ کرے گا in order to see the functionalities and requirements of these circuits and the processes that are carried out in the industry. So let me proceed further. So first of all, we want to see how the voltage measurements is done. In this first section, you will see how DC millivolt meter or AC millivolt meter is implemented using operational amplifier, and what are the requirements of the voltmeter, and how this voltmeter works to measure the millivolts of the input signal. And then we will see a display driver and instrumentation amplifier. So these topics you can see in section 11.5 of your textbook, Electronic Devices and Circuit Theory. Instrumentation circuits are popular area of op-amp applications is in instrumentation circuits. So op-amp has a very wide applications in these instrumentation circuits, such as voltmeters, drivers circuits, and instrumentation amplifiers and much more. So this is a simple op-amp circuit which is used to measure the voltage of the source that is applied as V1 at the input, and this voltage is measured using the circuit, and the voltmeter indicator will show connected at the output of the op-amp the reading of this input signal. So in this circuit, you are using a 741 op-amp which is connected as a DC voltmeter. So we will see how this circuit works and how it displays its reading at the output corresponding to the input. So first of all, note that the input impedance of the voltmeter is high. An ideal voltmeter should have very high resistance to avoid loading effect of the meter. So मीटर की जो इंटरनल रेजिस्टेंस होती है वो बहुत हाई होनी चाहिए ताकि लोडिंग इफेक्ट ना हो सके। जो वोल्ट मीटर में जब आप वोल्ट मीटर को किसी भी सर्किट में कनेक्ट करते हैं तो उसकी वजह से जो रीडिंग है वो आपकी चेंज नहीं होनी चाहिए जब आप मीटर को सर्किट में इंट्रोड्यूस करते हैं। तो इस सर्किट में अगर आप देखें तो इसकी जो इनपुट इम्पीडेंस है यहाँ पे वो इट इज़ अबाउट 100 किलो ओम। सो इनपुट इम्पीडेंस ऑफ दिस सर्किट इज क्वाइट हाई, नॉट द आइडियल बट इट इज इन hundreds of kilo ohms. So it is 100 kilo ohms, which is quite high. Secondly, sensitive ammeter is used at the op-amp output to give the voltage reading corresponding to the input level. So voltmeter, a sensitive ammeter, milliammeter movement is used. This meter is a galvanometer, which whose reading would be shown when a current flows through this meter. So it is a current sensitive meter, and its meter movement is based on the current that flows through this meter, and depending upon the magnitude of the current, this meter shows the deflection corresponding to this current. The transfer relationship would be required to establish this relationship, that is the relationship of voltage, input voltage and the corresponding meter current, to establish a relationship to give the reading of the meter corresponding to the input level, how much the input level would be and how much the corresponding output current through the meter to indicate the meter reading and give me the corresponding level of the input. So that output current, which would be function of the input voltage applied to the meter input terminals, to give me the reading of that input magnitude or input level. So for that, the transfer relationship would be required to establish this relationship for measurement, and it is shown in the next slide. So we want to derive a relationship of the input voltage and the output current. The relationship of these two quantities will give me the corresponding reading of the meter movement connected at the output of the op-amp. So in order to get this relationship would look like this, and we will derive this relationship in this slide. So this is the relationship that we want to establish, that is I out over V1, I out is this current, and V1 is this input voltage, and the magnitude of this ratio would be equal to Rf over R1 into 1 over Rs. Rf is this resistance, R1 is this resistance, and Rs is this 10 ohm resistance connected at the output. So first of all, we can see that this op-amp configuration is op-amp is connected to negative feedback, and this configuration is a configuration of that we have seen inverting amplifier, in which output of the op-amp is connected through this resistance to the inverting terminal of the op-amp, and input is applied at the inverting side. So this op-amp is connected as an inverting amplifier. So from the previous classes, we know that the output of this inverting amplifier here at this point would be equal to minus Rf over R1 into V1, where Rf is this resistance, R1 is this resistance, and V1 is the applied voltage. Also IS is this current through this resistance source. This is IS, and this current is equal to V0. This is voltage V0, and this is current I0. So I0 would be equal to, IS would be equal to V0 over Rs. So current through this resistance would be equal to the voltage across this resistance, which is V0 divided by the resistance value. So this is the current IS. Now we assume that IS is equal to I0. From this, this is I0, this current is IS, and if I assume that this current I0 is equal to IS, that is no current is flowing in this path, then we can write from this equation as I0 would be equal to V0 over Rs, which implies that V0 would be equal to I0 into Rs. So by putting the value of V0 from this equation into equation 1, that is V0 here, so we can write it as I0 into Rs would be equal to minus Rf over R1 into V1. So we just plug the value of V0 here on this relationship, which is I0 into Rs. So I0 into Rs is equal to minus Rf over R1 into V1. And from there I can take Rs to the right hand side and V1 to the left hand side, then I will get I0 over V1, that would be equal to minus of Rs over R1 into 1 over Rs. And then taking the mod, we get this minus sign would be would be muted, and the mod of this value will be equal to RF over R1 into 1 over RS. So what this ratio will tell us that how much the current would be, output current would be as compared to the V1. This ratio will give me the ratio of current to the input voltage. So for given values of the components in the previous circuit, with these components values, this ratio would be equal to 1 milliampere divided by 10 millivolts. That is, the output current would be 1 milliampere corresponding to the 10 millivolt input. So for an input voltage of, for example, 10 millivolts, will result in a current of 1 milliampere. If the input is 5 millivolts, then the current through the meter would be 0.5 milliampere, which is the half-scale reflection. So if input is 10 millivolts, then the meter will show the full-scale reflection of 1 milliampere, and if input is reduced to half, then the meter deflection would reduce to half, corresponding to the input voltage. So for example, if I am having this meter, and this is for example 0 reading of the meter, and this is the full scale reading corresponding to this meter of 1 milliampere. So this is 1 milliampere value. So if input is applied 10 millivolts, then the meter will show 1 milliampere. If input is applied input is applied 5 millivolts, and current would be around midway at 0.5 milliampere. Now, if we change the value of resistance RF to 200 kilo ohm, this RF is initially it was 100 kilo ohm, and if it is now increased to 200 kilo ohm, then the ratio would become 1 milliampere divided by 5 millivolts. That is, for an input of 5 millivolts, the meter will show full scale deflection. So showing that the meter now reads 5 millivolt as full scale. Similarly, you can look for the AC voltmeter and display driver in the corresponding section and go through those applications as well. And now we are going to see similar conditioning circuits, and why these similar conditioning circuits are required in our industrial applications. So for example, you have any process and you want to add some physical quantity in a process, then you take that input physical quantity, and for example temperature, pressure, some liquid flow or light, etc. And this device, which is a transducer, which converts that physical quantity into an electrical quantity like voltage, current, or resistance. Now here I want to emphasize why signal conditioning circuits are required. The reason is the transducer will produce an electrical output signal, which is either voltage, current, or resistance. First of all, ADC takes an input as voltage, but if the output of transducer is not a voltage, if it is current, then you required a circuit which convert this current into voltage that is required to the ADC. Similarly, if there is a change in resistance of the transducer due to the variation in the physical quantity at the input, then again this change in resistance is required to be converted into voltage, which is given to the input of the ADC. And secondly, the output produced from the transducer, the magnitude of the output, either it is voltage, current or resistance, is very small. The change in these quantities is very small. So it is required to amplify these the output of the transducer before it is applied to the ADC, because ADC requires relatively high voltage levels to operate, typically 0 to 5 volts or minus 5 to 5 volts. So we need to introduce a signal conditioning circuit block between the transducer and the ADC, so that this signal conditioning block either translate low level signal produced from the transducer or amplify it, and secondly it can convert current into voltage or resistance into voltage that is to be provided to the ADC. So other than these two functionalities that signal conditioning circuit needs to be performed, there are some other important features that are required to be signal conditioning circuit to do this function of translation of the signal from the transducer to the output of the signal conditioning circuit. So function of instrumentation circuits or signal conditioning circuits are number one, interface or isolation. It should provide an interface between the transducer output and the ADC input, and secondly, isolation is required to be produced from the transducer to the ADC. Next is amplification, and then current to voltage conversion and resistance to voltage conversion. A circuit providing an output based on the difference of the circuit that performs these type of functions can be implemented using some circuit component the function that is performed by to perform the signal conditioning task, the circuit or module that is used to perform this functionality is called the instrumentation amplifier. So what is instrumentation amplifier? A circuit providing an output based on the difference of two inputs times the scale factor is called an instrumentation amplifier with following features. So instrumentation amplifier is nothing but a difference amplifier which amplifies the difference between two inputs and provide an output. So the difference amplifier must have the following features to be used as a signal conditioning circuit. Number one, it should have a high input impedance, large common mode rejection, finite accurate and stable gain with low temperature coefficient, easier gain adjustment, low DC offset, low output impedance, and high slew rate. We will come to each of the characteristic of instrumentation amplifier one by one as we go along. First of all, the instrumentation amplifier must have high input impedance. This feature is required to be for a signal conditioning circuit, because signal conditioning circuit has to be interfaced with the transducer, and the transducer which produces the output due to the change in our physical quantity. This corresponding output from the transducer must be accurately measured by this instrumentation circuit, so that the change in the physical quantity must be correspondingly so whatever the change in the physical quantity must be accurately measured by this signal conditioning circuit, and this output should not be changed or modified when a circuit is being interfaced in order to measure this quantity. The second important characteristic of the instrumentation amplifier is the large common mode rejection, because we want to amplify the difference of the input signals, and the common mode signals must not be amplified. So common mode rejection ratio of the amplifier should be high. Then we have the finite and accurate voltage gain, stable gain of the amplifier. The gain should not be changed with a change in temperature, so that the temperature coefficient must be low, and the accuracy of the gain should be very high, because of we are measuring the quantities that are governing the process of a plant or an industrial process. The accuracy is very important to carry out the process in a precise manner, and then we must have the easier gain adjustment for the amplifier. So amplifier gain can be controlled by some easier mechanism. Then there must be low DC offset and low output impedance for the circuit that is to be interfaced with the ADC and high slew rate. These two parameters, low DC offset and high slew rate, that we will introduce later on when we study the practical aspect of operational amplifier. So when practical op-amps are considered, then these two quantities will be introduced here. So you can go through this slide to have what I have discussed in the previous slide, that what is the consequences of these characteristics of the instrumentation amplifier upon the measurements of the quantity, that is what should be the accuracy about the gain and stability, then its gain adjustment, the high input impedance, low output impedance, common mode rejection, and the high slew rate. So usually the instrumentation amplifiers are used to measure some physical quantities. This is the one of the approach in which our physical quantity is measured using a Wheatstone bridge, in which a transducer, which in this case is a strain gauge, which measures the pressure, is used as a one leg of a Wheatstone bridge, and the other three resistors are of some unknown values. These two resistors are fixed, constant resistors, and this one is variable. And at a certain condition, this bridge is balanced by this potentiometer for a given value of resistance without applying any pressure at normal condition. This bridge is balanced by adjusting the potentiometer, and so that the potential difference between these 2 points is made 0, that is Vg. Vg is 0 when bridge is balanced. So if there is some offset, then you can use this potentiometer to adjust this reading, so that this meter should read 0 current when there is a potential difference between these 2 points that are middle of the bridge. If these 2 points are at equal potentials, then no current will flow between these 2 points, and this bridge will be balanced. Now, with some pressure applied, and the bridge becomes unbalanced, then a potential difference is created between these 2 points, between VA plus and VA minus, and whatever the difference is produced, you want to measure this potential difference, and this is the one approach by which you can measure this difference and produce an output which depends on the difference of these 2 potentials that are applied to a difference amplifier. So this is a difference amplifier which basically takes these 2 inputs and produces an output which will be the difference of these 2 inputs. Now, a problem with using a difference amplifier of kind this is that as you can see that the input impedance is low, because the inputs are applied through these resistors. As you know, whenever the input is applied through resistors, there must be a current, finite value of the current, and the value of voltage, and the ratio of voltage and current will give the input impedance. So as there is some finite current flowing through these resistors, when you apply voltage at each terminal, then the input resistance or input impedance of the circuit will not be high, it will be low depending upon the values of these 2 resistors. So you can see that the input impedance is low, and to improve the input impedance, what we can do is we can introduce 2 op-amps at the input side. So we can introduce op-amp at the input side to improve the input impedance, as we have seen in the previous classes, that we introduce then we apply input here to the difference amplifier. We introduce an op-amp and apply input to this point, and for this op-amp and for the bottom op-amp we apply input here. So this is the input that is applied from the Wheatstone bridge. These are the 2 terminals coming from the Wheatstone bridge, and then one input is going to this top op-amp, and the second input is going to the bottom open, and the inputs are now directly applied at the non-inverting terminals of the open, so that the input impedance is now very high and it approaches infinity. So this is how the difference amplifier is modified to increase the input impedance by introducing these two op-amps at the input side, and now the inputs are coming from the these two gates and applied on the each input of the op-amps. Now let me see how this instrumentation amplifier works and how its output is produced when we introduce these two op-amps at the input side, and the combinations of resistors which are introduced as well. And now this new circuit which has three op-amps and a number of resistors, this performs a circuit which produces output which would be difference of these two inputs and some amplification factor determined by this constant term, which depends upon the values of these resistors. This resistor R is this one, and these are R of some values, and this RP is connected as a potentiometer. This is the potentiometer RP. P stands for potentiometer, and this is a variable resistor that is introduced. Later on we will see that you can adjust the gain of the circuit using this potentiometer, and the circuit will produce an output that would be difference of these two inputs with the gain controlled by this potentiometer. So we have seen that these two parameters of the instrumentation circuit, that one is the high input impedance that we have obtained by introducing the two op-amps at the input of the difference amplifier. Then we have introduced a gain, produces a gain which is adjustable and have a finite value depending upon the resistors, and it can easily be adjusted. So again, this will become easy, and these are the features that we have incorporated into the op-amp, into the instrumentation amplifier, and it would have a large common mode rejection that we will see later. How the circuit is producing an output which has a common mode component, having a common mode component low as compared to the difference components. That is, this circuit will amplify difference signals largely as compared to the common mode signals. So first of all, let me analyze the circuit and develop a relationship V0 defined by this equation. How this equation is produced by the circuit that we are going to analyze. So as you can see that the input impedance is high because of the inputs are applied at the non-inverting terminal. Gain would be accurate and stable because of the negative feedback, and potentiometer is used to permit adjusting the gain of the circuit, and a single quad op-amp IC can be used along with the resistor components to build the circuit. So coming to the analysis of the instrumentation amplifier, again we assume that the output does not go into saturation and the virtual short circuit condition is valid for each op-amp. As you can see that each op-amp is connected in the negative feedback. Op-amp number 2, you can see that the feedback output from this op-amp is connected to the negative terminal through these resistors. Similarly, for A1 op-amp, the output is again feedback towards the negative terminal, and for A3 again output is connected through this resistor to the negative terminal. So in all these three op-amps, negative feedback is connected. So for amplifier with the negative feedback, and if output is not going into saturation, then there is always a virtual short circuit between its two inputs of the op-amp. So with this assumption, both input terminals of the op-amp would be at the same potential. Secondly, the current in each terminal of the op-amp will be 0, as we are applying these conditions for each of the circuit which have negative feedback. Next is towards the analysis. What we do is we define nodes VA and VB right here. VA is defined here and VB is defined here, and the current I through the indicated direction. This is the current that is defined in this direction. This current is also I, and this current is also I. You can see that current through the three resistors would be equal, because there is no current into this path, because this is the input terminal of the op-amp, and the current into the input terminal, we are assuming that it is equal to 0. Similarly, current through this link is also 0. So whatever the current is coming from this point towards the so whatever the current is coming from this node, it flows through all the resistors equally. So next is the output of op-amp A1 is defined as Vx. The output of op-amp A1 is defined as Vx, and output of A2 is defined as Vy. Also note that the current is equal in each resistor, because the current is in the inverted terminal of each op-amp is 0. Now we can apply the Kirchhoff current law at each node. First of all, at node VA, we can apply current law here, that entering into this node is also equal to current leaving that node. So this current I is entering, this current I is leaving. So both currents are equal. So this current, both currents will be equal. That entering is equal to current leaving. Now what will be the top current in the top resistor? That is resistor R. The current in this resistor is defined as Vy minus Va over R. So keep in mind the direction of the current. This is the conventional direction of the current, and it is defined in this way. So its value would always be, we would be considering the higher potential as Vy and lower potential as Va. So Va minus Va over R would be a positive current I that would flow into the resistance. Similarly, that would be equal to current flowing through Rp, that is current through this resistance would be equal to Va minus Vb over Rp. So this is Va minus Vb over Rp. So we can rearrange this equation as Vy over R minus Va over R equal to Va over Rp minus Vb over Rp, and knowing the fact that Va would be equal to V2, you can see that this voltage Va would be equal to V2, because voltage at these two terminals of the op-amp are equal. So this voltage is defined as V2, so other terminal voltage will also be V2. Similarly, voltage at this terminal is V1, so voltage at this terminal will be also V1, and through this connection, Vb would be equal to what? Vb would be equal to V1. So Va would be equal to V2 and Vb is equal to V1. So VA into V2 and VB into V1. So by putting these two values of V and VB in this equation, then the VA in place of VA we will write as V2, and in place of VB we will write as V1. So from this equation we can write this equation for Vy. So bring other term onto the right side, then Vy over R will be equal to this. From this we can find out Vy is equal to, and this R will go to the other side and multiply with each term. And then finally by combining the like terms we will get Vy will be equal to 1 plus R over Rp into V2 minus R over Rp into V1. Similarly, we can apply KCL at node VB. This is node VB. So if I apply KCL, then this point will be equal to this, and then when we find the value of I through Rp, then this will be VA minus VB over Rp, and for the current through this resistance R, the value will be VB minus Vx over R. So this is VB minus Vx over R and VB minus VB over Rp. Similarly, when you further manipulate this equation in a similar way that we have done for Vy, we can write the expression for Vx, that would be equal to 1 plus R over Rp into V1 minus R over Rp into V2. Now we have obtained equation Vy and then Vx. Call this as equation 1, and for Vy call it as equation 2. Now as we know that the op-amp A3 is connected as a difference amplifier with inputs Vx and Vy. So output of the op-amp A3, which is connected as a difference amplifier, will have an output that will simply be difference of these two inputs Vx and Vy. So this is the op-amp A3, in which this is the output, and the input is applied as Vy and Vx at non-inverting side and Vy as inverting side, with all these four resistors are of equal value. So output would simply be Vx minus Vy, as we have studied in the difference amplifier in the previous class. So if the output A3 output of op-amp A3 is defined as Vout equal to Vx minus Vy, then plugging the values of Vx and Vy from equation 1 and 2 into equation 3, we will get Vout is equal to this is V1, this is Vx, from this to this point this is Vx, and then this is Vy with negative sign is being this term became negative and this became positive because of this Vy term is multiplied with negative sign here. So now if you rearrange this equation for V1 and V2, combine the like terms, you will get 1 plus R over Rp plus R over Rp into V1 minus, take minus from this term and this term, we will get minus into 1 plus R over Rp plus R over Rp into V2. So from here you can combine these two terms that as 1 plus 2 R over Rp, this is also 1 plus 2 R over Rp, then you will get 1 plus 2 R over Rp into V1 minus 1 plus 2 R over Rp into V2, and from which this term is common in these two equations, these two terms. So V out would be equal to take this common, then it would be 1 plus 2 R over R into V1 minus V2, which this is the equation that we were interested to develop for the difference amplifier. Lastly, we can also write this equation as V out equal to K into V1 minus V2, where this C is this constant is RD K, and it would be equal to 1 plus 2 R over RP. So this is the instrumentation amplifier with the features of having high input impedance and the voltage gain defined by this relationship, and it produces an output which would be difference of the inputs, and it has a high common mode rejection and low output impedance. The gain would be stable, and its value can be adjusted by varying the potentiometer resistance. Now let me do an example. This is the instrumentation amplifier with the component values given, and these are the 3 op-amps which are connected in negative feedback, having these two inputs V1 and V2. And you are asked to calculate the output voltage expression for the circuit shown in figure below. So, see, this is the output voltage expression that is required to be calculated as we have derived the relationship for the circuit as V out is equal to 1 plus 2 R over RP. These are all the same values and are defined as R, and this is the potentiometer value RP, and these are the two inputs V1 and V2. So plugging these values of R and RP, R is 5 kilo ohm, so 2 into 5000, and RP is 500 ohms, so this is 500. So if we simplify this equation and compute the result, then we will get 2 into 50 is 100, 100 divided by 5 is 20, 20 plus 1, 21. So 21 into V1 minus V2. So this would be the result. So that's it for today, students. Thank you very much. Take care. Allah Hafiz.